In this unit, we're going to study exponential function. And the standard form for exponential function is y equals a times b raised to the x. And notice the location of the variable x, the independent variable x. It's in the exponent. That's why it's called exponential function. Also note that in this case, the base b under that x makes a huge difference in terms of the shape of the curve when you graph it. When b is greater than 1, the exponential function is an exponential growth in function and in increasing. So this is exponential growth, and it's increasing. And if I'm drawing it roughly, it grows like that. And when the b is less than 1 but greater than 0, the function is exponential decay. And it's decreasing. Decreasing meaning as x goes up, y comes down. So it actually looks something like this. And we're going to study further about the shape and the behavior. Asymptote is a line which the graph gets closer and closer and closer to, but never touches it or cross it. So let's see. It's a line which the graph gets close to, but never touches. Or never crosses. Okay, let's look at the first example. It says, classify as an exponential growth or decay, create a table of values and graph, then identify its key characteristics. So the function is y equals 2 raised to the x power. So let's see. We have to classify it. Remember the standard form is a times b raised to the x. And if b is greater, in this case, b equals 2, which means b is greater than 1. So this is exponential growth function. Okay, circle growth. Next, so we did this part, and then we have to create a table. So we have x and y. I always start usually with 0 or 1 or -1. However, I put in there into x to make my life easier. So if I do y equals 2 raised to the 0, anything raised to the power of 0, y equals 1, right? From there, I do 1, so y equals 2 raised to the power of 1, and that's obviously 2. And then if I do 2 is 4, y is 4. And I can also go negative. Remember, negative exponent, all it does is bring that downstairs. And so I have 1/2. 1/2 is 0.5. And if I put in -2, so y raised to the -2, then 2 squared would come down to the denominator. So that would give me 1/4, which is 0.5, right? Now I've got enough values here. I can start plugging. So I still like to go from 0, 1, and then it's 1, 2, then it's 2, 4 is here, and then it's -1/2, which is here, and then it's -2 1/4. So be very careful that this shape looks something like this. it keeps going like this, right? It will never cross the x-axis. Why is that? So notice here on the in the y values, first of all, they're always positive, right? As the x gets smaller and smaller in the negatives, it will get closer and closer to 0. But you will never find a situation where when there is a positive number raised to a certain power, whether that x equals positive or negative, this whole thing becomes negative. It's just not possible. So therefore, we're saying that this, I'm going to use red. This x-axis is my asymptote because that's the value, that's the line where that exponential growth function gets closer and closer and closer to, but will never cross, right? So the domain, therefore, is domain. Remember, I always say domain and range, I go by the alphabet order. In the alphabet, D comes first, R comes second. Therefore, domain is X and range is Y, because X comes first and Y comes next. So the domain is all X value. Whoops, time to get up, I guess. So it's all real numbers. Do you hear the alarm in my son's room? The range, notice that what's the range? The range is the y, and we said the y will never go below x equals 0. So the range is always greater than 0. The y-intercept, which is right here, if I use red, that's y-intercept, and it's also here, right? So it's when x equals 0, y is 1. And the asymptote is y equals 0. That's the line on the that's the x-axis. That's what it is. X equals 0. I'm sorry, y equals 0. Oh, that reminds me. Be careful with that. When you look at the x-axis, it's actually y equals 0. Think about it when this is something we talked about in Algebra 1. But when we look at the y-axis, that's when x equals 0. And same thing when you look at a vertical line, it's x equals a constant, right? Let's look at the next one. In this case, we have, remember, y equals a times b raised to the x. In this case, b is 1/4, which is between 0 and 1. And in this case, this is an exponential decay function. And the domain and the range and all of that we have to find through graphing it. So let's try this. I will start the same trick. When I put in 0, anything raised to the power of 0 is 1, right? Then if I put in 1, y equals 1/4 raised to the power of 1. Then it's that number itself, which is 0.5 or so. And when it's 2, it becomes 1 squared over 4 squared, so it's 1/16. So you can tell it's getting smaller. And then if I do negative, y equals 1/4 raised to the negative. I like this much better because that negative exponent allows me to flip it, and then I have 4 here. And then when I have -2, is the same thing. I flip it first, but I keep the power, right? And I should have 16 there. So now let's graph it. I have 0, 1. I have 1 1/4, so 1 1/4. Ooh, these are small. And I have 2 1/16. It's almost 0. And then on the other side, I have -1 and 4. 1, 2, 3, 4 here. I have negative 2, 16. So I know that's negative 2 is here. 16, I know here is about, here is only 10. So 16, I have to go up. And so it's somewhere here. So in other words, this shape, look at this. In order to connect this, it's not the easiest thing to connect. This is, I have to take this, come all the way down, and then bent there. There we go. So again, notice on the y, it never goes below 0. The y value is always greater than 0, right? So that's the observation that's on the table and on the graph. So that's why we said is always greater than 0. X, it can be anything. X can be, you can say X belongs to real numbers. You can do that, or you can simply write it out, all real numbers. The y-intercept, we said, is right here. When x equals 0, y equals 1. There it is. And the asymptote is the x-axis, which is y equals 0. All right? So this takes some practice. Take your time. We'll do more practices soon. Now let's look at some more complex problems. Number 3, y equals 3x minus 1. We probably know how to graph, not probably, by now we do know how to graph y equals 3 raised to the x. We just added a piece to it. So let's see, what should we do about it? First of all, let me get the color right, blue. The standard form is still a times b raised to the x. And in this case, b is 3, which is greater than 1. So therefore, this is an exponential growth function, right? Now, let's do the table. We start from 0. If I plug in 0, so I have 3 raised to the 0 minus 1, which is 1 minus 1. I have 0. If I put in 1, that's 3 raised to the 1 minus 1, which is 3 minus 1. I have 2. So I have, the final answer here is 2. And if I plug in 2, I would have 8. Plug in negative 1, I should have negative 0.666 is negative 2/3. And if I plug in negative 2, so it's negative 0.8. 0.888. Okay, so let's see, how can we graph this? I have 0, 0, which is here. I have 1, 2, 1, 2. I have 2, 8. It's there. And on the negative side, I have negative 1, negative, a little bit more than negative half. I have negative 2, then I'm close to negative 1, but not quite. So if I have to graph this one, it will be like this. It's not the most prettiest graph. Okay, so from this you can tell that, look at this here. It's approaching what? It's approaching negative 1. That's my asymptote. So this is my asymptote, but it will never cross that line. So the domain is, what are the possible x values? X can be all real numbers, right? That's how we write x belongs to real. And the range is y cannot cross that negative 1, and y has to be greater than that. The y-intercept, if I use my red, is right here, 0, 0, right here. On the graph on the table, they're the same thing. And like we said, the asymptote is y equals negative 1. Okay, so that's number 3. I want you to pause the video, do number 4 on, by yourself, and I'll write the answers down here. Okay, that's the answer for 4. It's very much similar to number 3. And I also want to ask you to observe this pattern. So when we have just the standard form, let's say what we did on the previous page, y equals 3 raised to the x, or y equals 2 raised to the x, the asymptote was y equals 0, right? But in this case, once we add the standard form minus 1, notice the asymptote, and notice the asymptote here where I highlighted in gold. So that's when we're adding the a constant at the end of the exponential function. Basically, like I said, the adding or the subtracting is to raise the entire graph along the y-axis, lift it up, or bring it down by whatever that constant is. Okay, now I'm asking you to graph. Let me see if I can shrink this and move it up. I'm going to ask you to graph 5 and 6, and I will write the answer key here down. Remember to pause the video here. Okay, here are the answers for 5 and 6. Make sure you check your answers. If you make the mistake, bring it to class and ask the question, because I bet you everybody else may be making the same mistakes. This part is a bit difficult to digest because it's quite different from what we have been doing, but it's just more tedious. The fundamentals are still exactly the same. When you graph linear equations, quadratic equations, and now exponential functions, you always start with creating a table. And then linear equation is a straight line, quadratic is a happy face or a sad face. Exponential functions have exponential growth or exponential decay, okay? And this type of function probably, arguably, is the most useful in the short term in biology that you've probably seen either by design or by chance quite a bit. All right, I'll see you guys later. Take care. Bye-bye.